All right. Now we've got Xiangyu talking about stableKanren. Take it away.
It's okay. Yeah. All right. Good morning, everyone, and good morning to everyone watching from the U.S. East, New York, Boston, etc., and good night from Tokyo. My name is Xiangyu Guo. Today, I'm here to present our project on adding integrity constraints to stableKanren to make it to answer this kind of to be or to not to be decisions. Okay, let's get started. So outline for today, first is introduction, like why do we need these kind of features? Second one is preliminary about to understand the integrity constraints. Third one is how we extending the stableKanren. Fourth one shows the three useful examples about how to use this extended stableKanren to serve to solve some problems and some conclusion and future works. All right, so let's get started. First is the introduction. Okay, we're from miniKanren to stableKanren right now. So this is the standard miniKanren we all know about. It came with four operators: the unification equal, a flash to do the extension, combi to the disjunction, and the run to run the query. Okay, so the semantics of the miniKanren is the minimum model semantics. Then stableKanren just extended the miniKanren with two more operators, the final and the nodal. Nodal basically doing the negation things. The final is the new wrapper to wrap around the two go function into one. So the semantics behind this stableKanren is stable model semantics. Okay, so just give you a very simple examples. It's Alice and Bob, these two famous computer science persons. Okay, they are planning on the business trip, maybe coming to the ICFP, but unfortunately, only one of them can travel, either Alice or Bob. So this kind of problem, we can encode it in stableKanren as this program. So define no Alice. If Alice want to go, Bob cannot go, not all Bob. If Bob is going, not all Alice cannot go. All right? So to run the query, we can ask the question like, okay, can Bob go travels? Then stableKanren will answer yes. Is underscore dot zero is indicated success. Okay, it means okay, Bob can go. Then we ask another query like, can Alice and Bob go together? StableKanren says no, they cannot go together. All right. Now, you give a small taste. Now we really want to figure out okay, what stableKanren can do and what it cannot do. We will use a combination search problem as examples. Well, this is a very famous one. It's an n-queens problem. We try to solve it using stableKanrens. All right. So here, what stableKanren can do right now, it can do an explicit search approach. So from here, we can say queens. So this one is okay, we use the variables to accumulate the answers. So the first two parameters, x and n, indicating how many queens we're solving right now. The n is the total queens we try to get. Qi, kind of input, the queen's input, means the accumulator start with the empty. Then the Qo is the output, okay? So base case is when the x reach zeros, we just unify the Qi and the Qo. So basically the accumulated answer is our final answers. Then we will say, all right, let's try to pick one queen and place it on the board, okay? And then try to verify they are not attacking with the existing queens. Like the Qi here, okay? Now we move to the next steps. Okay, we successfully placed it. They are not attacking with each other. We move to the next queens, go on and force until we reach the base case, the x will keep decreasing till 0, okay? How to pick queens, same thing, how to check the attack. So we basically need to check, iterate through, looping through all the existing queens so far, or we check if they are attacking each other on the same row, same column, diagonal. And then we wrap this interface into one n queens and a queue. So this is what I mean. Okay, this is the accumulator. Start with empty, and the final answer is the queue. All right, so far so good. Because it can solve the n queens problem, very decent, but the problem we showed in the previous slide, it did not fully utilize the nodal we introduced in the stableKanren. So the nodal we introduced in there actually can produce multiple models under stable model semantics. So actually, the line, like an auto attack, is under the stratified negation. I will define this one later. No worries. And also, as we have saw, that algorithm we're actually describing is step by step, kind of like explicit search, right? With guided search. Now we may wonder, like, can we do it using implicit search approach? So for example, here we are actually using the full power of the capability of these nodal things. We have like a pick. We go either to pick a queen or not pick a queen on the position X and Y. So this is a 4x4 board, okay? 4x4 board. We can either pick a queen or not pick a queen on a certain position, or this position is free. So this maroon and the gold pick and not pick, kind of like generate all the combinations from like no queens on the board to all 4x4 is the 16 queens on the board, all right? So it's amazing. We save a lot of work here. Unfortunately, this implicit search is incomplete. That algorithm was incomplete. Why? Because stableKanren right now cannot constrain the outcome of the pick and the free. So for example, among all the combinations, like obviously all the 16 queens we place on the board is not the answers we want. We try to filter out, eliminate the answers. So there's no way to do that. So that's why, like here, we try to use this thing called integrity constraints to control the outcome of the stableKanren scope function, or we call the predicates in logical programming, just in case you guys get confused with the predicate in functional or something, all right? So this is the implicit search we got from the previous slides, okay? Now we try to add something like, okay, we will introduce a new macro called constrainto and a new approach to compile these integrity constraints. And with all these enhancements, hopefully we can write something like this. It's called constrainto. If we pick something, pick two queens, then if they're on the same row, we don't want this. So this one constraint basically saying these two queens cannot on the same row, okay? This is the goal we try to achieve. And how do we do it? Let's have some like preliminaries like to lay some foundations. First, go back to the normal program and the stable model semantics as a quick recap. So to define a normal program, we actually start from the definite program. This is what miniKanren has right now. A definite program is like in this form. It's like A as the header to a bunch of like body, B1 till the Bns, where they are all atoms. Atom can be evaluated as true or false, okay? Then all the definite program clauses can combine into a definite program. So for stableKanren, we actually support the normal program. Normal program is nothing special, but with this one, not, where's my pointer? Okay, not, okay? The rest are the same. So A, B, they all like atoms, but with the not and the B becoming kind of like called literals. So this is normal program, what normal program looks like. Now the semantics in the normal logic program. This is one I borrowed from the previous stable-Kanren slides. So basically, inside all these things, we have a set of atoms called an unfounded set in the normal program that can help us to categorize the normal program and their corresponding semantics. So for unfounded set, basically saying like tons of the atoms inside the unfounded set are only cycling support each other. So for example, we can say A is true if B is true, B is true if C is true, C is true if A is true. Now coming back, like there's no external support to say, okay, all these circular proof to be true. So the whole circle becoming false. So this is called unfounded set. Then based on this unfounded set, we call the loop, and the combination of the negation, we can kind of like categorize our normal program into this like type program, stratified programs, okay? So a type program is like, okay, they only have negation, no loops, all right? So for stratified negation, it has loops, but it does not combine with the negation. So if you have one level of negation, then the next is the loop, then another negation is okay, it's a stratified. Then eventually we will have like this like normal program without any restriction. Like you can combine a loop and negation together. So now we go back to our n-queens examples. As I mentioned before, that nodal attack actually didn't fully utilize the nodal ability in stableKanren. It actually was stratified negation. So let's see like, why it's stratified. So here we have one nodals right here. and it use like attack. And inside attack here, as I mentioned, it kind of like a loop, just looping through it. Then it didn't go back to use any nodal or something, right? So we categorize this as a stratified negation. So now, what's the stable model semantics? Some tons of definition, just for recap. Stable model semantics, it basically create a propositional image, these steps, to eliminate all the variables in there, just kind of like grounding, turn the predicate logic into the propositional logic, then create tons of like readout program to see if the model create that readout program is actually the minimum model of that readout program. If it is, then it's a stable model. If they have not matched together, it is not a stable model. So using the Alice and the Bob examples, as examples, we can try to see how stable model semantics works. So first we convert it into the logic representation, so it will be easier to discuss, okay? So these two things are equivalent, just two different representations. And we can say, okay, right now, because they're already in the propositional form, so the propositional image actually is exactly the same as the original program, okay? There's nothing special here. It's still saying like, okay, not Bob, imply Alice, or not Alice imply Bob. So we try our first interpretation. It's like, okay, is Alice and Bob going together? So this is our first interpretation. Alice and Bob are supposed to be true. So to create this radar, we just replace these two in the propositional image as bottom. Why? Because in the model we're already saying they are true. So not true means false, right? It's a bottom. So the readout program we have here is like, okay, bottom imply Alice, bottom imply Bob. So the model of this readout program is empty set. So this M1 prime, it does not equal to the M1 we use here to create it. So this model is not a stable model of the original program, okay? Another example is, okay, how about we put a Bob here as one of the interpretation. So the readout program we create will be bottom imply Alice, and Alice, because Alice don't show up, it can be top imply Bob. So this is the readout program. Oops. This is the readout program looks like. So in this case, the minimum model of this readout program is Bob. So it's matched the M2 we use here. So it is one of the stable models. All right. So it's just one simple examples. Now we can finally define the integrity constraints. So integrity constraint actually is the special form of the normal program clauses. But one thing to notice here, this term constraint we use here is different from the constraint logic programming CLP. The constraint logic programming, the CLP, that constraint actually focus on the domain of the variables. So sometimes I will call it variable constraints. But the constraint here, in integrity constraint, actually focuses on the truth value of the predicates. So I prefer calling it predicate constraints, but the logic programming people say you must call it integrity constraints. Okay, anyway. So this is our normal programming, normal program defined definitions. So this is what the integrity constraint definition will look like. It almost exactly the same, except for the head. Instead of an atom here, it implies the bottom. Okay. So for integrity constraint, the head of the clause is bottom, false, instead of an atom. So this one means like, okay, integrity constraint here is the headless. So this headless thing is actually some problem here in stableKanren we will try to resolve. I will mention why later. How this integrity constraint works is like, okay, the constraint is violated only if all body literals are evaluated as top. When a clause's body is evaluated as top, we got a formula that says the true imply false. So this logic statement basically does not help, right? True imply false. So we're saying, okay, all these literal cannot be true at the same time. So for example, not bn plus 1, this one cannot be true. So which means like bn plus 1 cannot be false. Okay, thank you. So this is one of the example of integrity constraint, like how we use it. So same thing, we converted the free and the pig, where we describe a 3x3 board, and we already know how to generate all the combinations. And we convert it to logic encoding. So this is in logic programming. This is what it looks like. Okay. The examples, I would just skip through it. Now they have like two approaches to handling this like integrity constraints right now. We will try to see if anyone can work in stableKanren. If it works, it simplifies our lives, but if it doesn't, we need to come up with our own solutions. The
Test.
much better? Yeah. Yeah, so since those two approaches doesn't work, so we will try to come up with our own approach to extending the stableKanrens. One possible idea is like, okay, the existing one is very good. It's just the transformation may have some problem. Can we just fix that? So from here, we can say, okay, because the headless in the stableKanren, it requires the head to create a go function. How about we convert the headless rules into a contradiction? So here we bring the A back, but there's not A at the bottom or at the tail. So this basically is the alternative integrity constraint. Is like we're using the head of A to create some kind of the odd negative loops. It kind of introduce a contradiction. Like if everything, all the literals in between becoming true, and this kind of saying like A and not A going to be true at the same time. It's impossible. So this is a contradiction. We try to introduce one. Then we also like modify the resolution. Where you need to change it from like proving the answers to checking all the proven goals. This is not very good for multiple reasons. Like first we still like generate that in a test approach. Wait until the last minutes. It cannot terminate the search in as early as possible, right? We want an approach that can terminate the computation early, and we don't want to ground in all the pairs of constraints. So we treat the integrity constraint as the resolutions exceptions. So we categorize like the body, the BI we saw in this definition as like two parts. One is the emitter and the other is the verifiers. And all the verifiers we can combine together as the constraint handler. So once the constraint handler evaluated it to be true, means like, okay, the constraint is violated, we need to terminate the resolution. So this is one of the examples like we showed previously. So this is one constraint. Here we have like two emitters, the peak XY, peak UV, two verifiers, X equals U, Y not equal Y, Y not equal V. Then this is the constraint handler. Constraint handler basically just concatenating all the verifier together with the top. So once everything is true, then it's violated. All right. We converted it back to the our stableKanren representation. So here we all use like logic programming. We're back to the stableKanren what we love. Now this is the thing that we want to have. Like, okay, constraint though, new macro, green part is the emitter, blue part is the verifiers. Okay. Now we have everything. This is what stableKanren abstract level looks like. The definer here basically just wrap the two goals, the positive goal and the negative goal together into one. So the emitter actually need to emit some values to update those constraint handler, right? So we want to do some like constraint updater and constraint checking in this definers. And the whole resolution process looks like this. Okay, this is the previous stableKanren resolution, and we have all the constraint updater and the checker inside. Now, how the constraint is being updated, it's basically a continuation. So here, this is the orange part is a continuation. We don't have any value yet. It's just waiting some values, right? So how we do it, for example, when emitter emit x and y is 1 and 3, u and v is 2 and 4. So this continuation just gather values, we wrap around. So we can create another internal macro to create this like kind of a wrapping by like cascading the callings becoming like this, okay? Now we extended the miniKanren. Now let's try to see how useful it is. It turns out it's very useful because it enabled the new paradigm of solving the combinatorial search problems using these kind of integrity constraints. So it's a general steps, 3 steps to solve this kind of problems. First one, we model the problem as a graph. Second one, we're generating all combinations of the nodes and the edges, like pick and not picks. Then we're pruning out these unwanted solutions using the constraints from the solutions property. For example, n queens, they cannot attack each other, and we will see graph coloring and Hamiltonian cycles. So we show like, okay, the general approach to solve this problem, like we don't describing how to solve the problem anymore. Instead, we describe like what property we want to see from the answers. Then the stableKanren will like try to find all the answers to meet that property for us. Now we show this like, okay, the same solution, the beautiful of the relational programming, we can run for multiple purposes. So here is one example, okay, back to n queens. Right now we have the new constraint though, we add here, right? So 3 constraints, row constraint, column, and a diagonal. Okay, then we also constrain the minimum queens because for the 8 by 8, for example, 8 by 8 queens chessboard, we can play like 4 queens on the board still be a valid solution. So we want to
Is there a place for our variable, traditional miniKanren variable constraints as well as integrity constraints? Both, can they coexist and can they benefit from each other?
Yes, I think this question, logic programming community trying to solve. They have a paper calling like towards integrating a CLP and ASP is towards, because they still try to define the semantics for that. Because it's like a negation and you know, greater than or equal to, need some negation. But if you don't want these two parts, like two programs, to mix together, you want to have an integrity constraint and your inequality constraint separated. It should be done easily because right now they are not interactive. But if you want to say, okay, not x greater than or equal to 5, now we probably need some semantics, the proper semantics for that situations. Yeah. Thank you.
All right, maybe one last question. All right.
So I guess your solution, you have to split these things into emitters and checkers. You know, can you always do that? Does everything always decompose that way?
Yeah, it's a very good question. Of course, we can always do that because this integrity constraint, it try to constrain, like I said, the goal functions. So we can always tell, okay, this part is the goal function, like it already exists in the stableKanrens, and the rest verifier, it should be the Boolean expressions, right? So yeah, emitter just emit out the values, and so if we send it into the Boolean verifiers, then just verify it.
Thanks again.